Let's start by reading the exercise. From all the open boxes whose volume is 32 cubic centimeters, compute the dimensions of the one with the least surface area. Certainly a picture could help. Here's the box. X is the width, Y is the length, Z is the height, and they're all in centimeters. And this is an optimization problem with constraint. It's going to be a minimum problem because of the word least. We want to identify the constraint function and the target function. Let's start with the constraint. The constraint says that the volume is 32. Volume is width times length times height. So that says that x, y, z equals 32. What we want to optimize, or in this case minimize, is the target function, and that would be the surface area. Now, the word open means that it has a base and four sides but no top, maybe like an aquarium. So the surface area will be, there's a base, and that's length times width, x, y. There's two rectangles, x by z, so it's 2xz, and then we have also 2yz. That's the surface area. And we can phrase this as a minimize problem. We want the minimum, curly braces, of xy plus 2xz plus 2yz, subject to the constraint xyz is 32, or sometimes I like to write it as something equals 0. This part is the target function. We call it f of x, y, and z. And the constraint, or at least the part that's equal to 0, I'll call that g of x, y, and z. I forgot to mention something. There are natural limitations. Because it's a real-world problem, the dimensions are positive. We should also add the conditions that x, y, and z are all strictly positive. Makes no sense for it to be flat. Okay, next step is to look for critical points. There's three equations in one which we can write as the gradient of the function f equals lambda times the gradient of the function g. Lambda is going to be a fourth variable besides x, y, and z, an auxiliary variable. And besides this, there's also the original constraint. Let's write them down. We're going to get four equations in all. From here, we'll get that f with respect to x is lambda times g with respect to x. And similarly for y, and similarly for z, lambda g of z. And the fourth equation is the constraint. Well, in general, it's g equals 0, but when I convert this to our particular case, what we will get will be f with respect to x, that will be y plus 2z. That's equal to lambda. G with respect to x is yz. Next one, with respect to y here, that gives us x plus 2z. And here we get lambda times xz. With respect to z, we get here 2x plus 2y equals lambda, and then it will be xy. And the original constraint, well, I'll write it in this form. xyz equals 32. Just like in the case of two variables, xy, we can get rid of lambda by dividing one equation by another. Let's say we divide the top one by the first by the second. We would get y plus 2z over x plus 2z So yeah, dividing first by the second equals lambda y z over lambda x z.